If z squared equals -3 minus 7i, find two complex solutions or roots using Euler's formula for complex numbers. Euler's formula expresses a complex number in the form of x plus yi in exponential form, which is the form r times e raised to the power of I theta, where r is the modulus, or distance the point x comma y is from the origin. This is the same as r in polar form, and the angle theta is the angle in standard form or standard position whose terminal side contains the point x comma y. Because we're looking for two complex solutions or two roots, we will provide two Euler forms or exponential forms of the complex number using two consecutive coterminal angles. And for this example, we will use the least positive coterminal angles. In general, to find n roots or n complex solutions, we provide n Euler forms of the complex number using n consecutive coterminal angles. The next step is to plot the point for the complex number -3 minus 7i on the complex coordinate plane. This would be the point at -3, -7, which I've graphed here in blue. Notice I've also sketched the reference triangle. Let's begin by determining r, where r is equal to the square root of the quantity x squared plus y squared, which gives us r equals the square root of 58. And now let's determine our two angles for the angle theta, where the first angle theta is going to be the least positive angle with its initial side along the positive x-axis and the terminal side the hypotenuse of the reference triangle. Remember, tangent theta is equal to the ratio of the opposite side to the adjacent side, which means the reference angle of the reference triangle is equal to arctangent of 7/3, but this would give us an angle in the first quadrant, and therefore to find this angle, we would have to add pi radians. Again, if we enter arctangent of 7/3 on the calculator in radian mode, we get approximately 1.1659 radians, which is in the first quadrant, and therefore our first angle theta is equal to pi plus arctangent of 7/3, which is approximately 4.3075. Again, the exact angle would be pi plus arctangent 7/3. And then to find the next positive coterminal angle, we need to add 2 pi radians, which is shown here. The approximate angle would be 10.5907 radians. The exact angle theta is 3 pi plus arctangent 7/3. Now that we have r and our two angles for theta, we can write the given complex number in exponential form by substituting the square root of 58 for r and the angles for theta. Notice here we have the exact angle for theta, which is approximately 4.3075 radians. And then here we have the second exact angle for theta, as well as the decimal approximation, 10.5907 radians. Now that we have the two exponential forms, we can determine the two complex solutions or two roots by taking the square root of the exponential forms or the 1/2 power of the exponential forms. And let's take the 1/2 power. And we'll call the two roots z sub 1 and z sub 2. Notice here we have the two exponential forms of the complex number to the 1/2 power. And because we don't have nice angles here, we could just enter this into the calculator and get our two complex solutions or two roots. But let's show some simplifying. First, let's raise the square root of 58 to the 1/2 power, which if we look at the work below, we can write as the 1/2 power of 58 to the 1/2 power. Because we have powers to powers, we multiply the exponents, which gives us 58 to the 1/4 power, which is equal to the 4th root of 58, which we see here as well as here. And then we have to multiply the exponent on e by 1/2. For the first root, that gives us an exponent of 2.15375i. And for the second root, that gives us 5.2953i. And again, because we don't have nice angles here, we are not going to get nice trig function values for the sine and cosine of theta, and therefore there's no reason to rewrite this in polar form as I've shown here. Now we'll go to the calculator and verify these two approximate roots or complex solutions. It is important to make sure the calculator is in radian mode as well as complex mode, entering in z sub 1 to 4 decimal places. We do get z sub 1 is approximately -1.5192 plus 2.3039i, and z sub 2 to 4 decimal places is approximately 1.5192 minus 2.3039i. Now before we go, I also want to show the calculations when we use the exact angles. So again, the only difference here for z sub 1 is we have the exact angle of pi plus arctangent 7/3, and for z sub 2, we have the exact angle of 3 pi plus arctangent 7/3. And notice how when raising this to the 1/2 power, we now just have a factor of 1/2 in the exponent, and we still have the 4th root of 58. And now let's go to the calculator and verify we do get similar results. So we've already seen this first calculation. Notice how for the second calculation, using the exact angles, there is a slight variation in the solutions or roots, but to 4 decimal places, we do still get the same results, which are shown here below. I hope you found this helpful.